In this presentation, we will talk about how we in the SMEAP laboratory worked for the porting of an application called the web app in a hybrid cloud deployment, in particular through Kubernetes and IBMi. So let's first see a brief summary of our presentation. We will first talk about the application that we ported to a cloud environment, which is web app. Then we will talk about the first type of deployment, which is a Kubernetes cloud deployment. We will talk about Quarkus, which is a Java development framework that we used for the creation of a microservice on IBMi. And then we will talk about the final stage of our deployment, which is a hybrid cloud deployment with IBMi. So let's dive in deeper into SMEAP Web App, which is an application that our clients can use to interface with our ERP called SMEAP, thanks to a browser or a mobile device. Web App is made of three components. The first is Web App Frontend, which serves the interface that our clients use and is the main application. Then there's AS400 proxy, which acts as a middleware between web app and IBMi and manages the communication between the two. And then there's H53 service, which is a microservice that handles PDF printing. So let's see the first type of deployment that we did, which is a Kubernetes deployment. And to reach this stage of the project, we used these four technologies. To the left, we can see Kubernetes and Helm, which were used for the structural standpoint of deployment, so to manage the structure of our application. And to the right, we can see Prometheus and Grafana. These two were used to monitor our deployment, our Kubernetes cluster, and for alerting in case anything wrong happened with our application. The main technology that drove this project forward was Kubernetes. Kubernetes is an open source system for container management and orchestration. This may sound a bit complicated, but let's try to break it down by understanding first the concept of a container. A container can be seen as an evolution of a virtual machine that is more lightweight and has better bootstrap times, which is extremely important in a cloud environment where applications and microservices are very frequently restarted. Kubernetes is based on an infrastructure as code paradigm, which means that we don't need to manually create Kubernetes components and objects, but to do that, we will just need to write code, in particular YAML code. In these YAML code, YAML files, there will be the specifications and the properties of the Kubernetes objects that Kubernetes will create for us. One of these objects is called a pod, and you can think of it as an abstraction of the concept of a container that adds some other functionalities that we will see in the next slide. Let's also remember that Kubernetes offers high availability, scalability, and adaptability. What does this mean? That in a Kubernetes cluster, so in many nodes that run Kubernetes and where our containers are located, these containers will each host a single piece of our application. And Kubernetes manages the communication between these containers and also their scalability. In case one of these components is stressed and needs to scale, Kubernetes will automatically create more replicas, more copies of the same container, and load balance the users or the traffic on these replicas. Now let's take a look at the web app pod architecture. We can see four main components, but let's start with the one on the bottom left, which is the init container. And it's also the first component that is set in motion when the pod is started. The init containers task is to set up the pod. So what it does is it downloads the WAR file of web app. Web app is a Java application, so it's distributed through a WAR file. It downloads it from our repository, the latest version, and it shares it with the main web app container. To share files between container, the Kubernetes object called the volume is used. In fact, containers are like virtual machines over completely neutral and separated environments. And to communicate, we need to use this concept of a volume that enables data permanence in our cluster to share the file plus some configuration files that are used for our application. The main component of the web app pod is the Payara container. Payara is an application server for Java applications that runs web app thanks to the WAR file shared through the volume. The last piece of the puzzle is the health check mechanism, which is made of two probes, one liveness probe and one startup probe. Kubernetes probes are objects which are responsible for the health check of our application, and they do so in various ways. One of these is to call an endpoint and perform HTTP calls and check the status of the response. If the response is an HTTP code 200, it means that the application is running successfully without any problems. But in case the code is a 500 or 400 code, the probe will wait for 2 or 3 more consecutive errors and then restart the application. This helps prevent errors or long periods of downtime with our application in case there's a bug or a crash. With the Payara container, the probes will immediately recognize it and restart the application. During our deployment and porting of web app in a Kubernetes cloud environment, we went through a series of stages of deployment. The first one, and the most basic, was the manual deployment, where we manually moved the configuration files and the WAR application of web app within the pod. Successively, we went to a Docker image deployment, and the Docker image is a way of specifying what should be run in a container and how. So we packaged the application WAR file and the configuration files inside of a Docker image, and we ran that as a container inside the pod. This type of deployment had some problems. In fact, if we needed to change the application version or configuration files, we would need to repackage another Docker image every time. So to solve this problem, we shifted to an automatic deployment that uses tools such as init containers, volumes, and configuration maps that we've seen in the last slide. Configuration maps are a way to share environment variables into containers and Kubernetes pods. And that person, we've said that Helm is the package manager for Kubernetes to help with deployment, upgrade, and rollback of applications. And you can think of it as the Kubernetes equivalent of Linux, Yum, or Homebrew. And packages created with Helm are called charts, and they can represent a simple microservice or a complex application. In our case, the entire application web app and its three components were packaged into a single chart. But what exactly does Helm offer that an automatic deployment that we've seen in the previous slide doesn't? Well, it's possible to inject variables and flow control inside of a chart. And the chart is made of multiple configuration files, the same YAML files that we've mentioned before. And abstracting some of these values helps us with managing our deployment. So to make an example to better understand this, think of one of our employees that has to upgrade a web app version that is installed on Kubernetes. Well, to do so with an automatic deployment, that person would need to go into the YAML files, search through hundreds of lines of code for the single parameter that specifies web app's version and change it manually, while risking to mess something in the file and break something. Well, thanks to Helm, we can abstract this information in a separate configuration file, for example, a .properties file, which will have a field web app version with a value of, for example, 1.10, and that person would just need to change that value execute an Helm upgrade command, and see Helm change and upgrade our application. Not only that, but Helm helps with upgrading and executing rollbacks with zero downtime. And to do that, Helm creates two instances of the same application. So to go back on the same example that we just did, we will have two versions of web app, one with version 1.10 and one with version 1.12, for example. And Kubernetes, and thanks to Helm, will move the users from the 1.10 version, which is the old one, to the new one, but only when the new application is stable and ready to accept users, and then it will destroy the previous version of web app. In that way, the end user wouldn't notice any difference and any downtime with our application. We can now see that with one simple command from command line, which is helm install web app and the name of the folder where the chart is located, Kubernetes automatically installs web app in a single command. So let's now see all the components that Kubernetes creates. So we can see pods, one for each component of our application. And then services, deployments, and replica sets are other Kubernetes concepts that we will not focus on. To deploy web app on a Kubernetes cloud environment, we use the Amazon Web Services, or AWS for short. In particular, we used three specific services. The first one is EKS, and EKS is the AWS completely managed Kubernetes service. This means that AWS does the setup and configuration for Kubernetes, provisions for us the Kubernetes nodes, so the machines that run Kubernetes, and manages all the updates and configuration of the Kubernetes software. This lets us focus on developing our application and not waste time for the configuration of Kubernetes. Not only that, but EKS is integrated with other AWS services thanks to Kubernetes charts, Helm charts, called drivers. So by installing a driver of another service on our cluster, we were able to use other AWS services such as EFS. EFS offers a managed file system that automatically scales. And this file system is extremely useful for managing logs and configuration files. For an on-premise installation of web app, we had to SSH into the machine and check out the logs manually. And for multiple installation, we had to change the machine, SSH into different machines, and keep checking these logs. AFS can aggregate logs from multiple clusters and multiple web app installations and mount the target directory in any computer, any Linux environment that we want. So if there's a problem with an installation or we need to check the logs, we can simply mount the EFS file system locally and check it out from there. That's also the same for configuration files. If you want to change the configuration of one installation of web app, we can do that thanks to EFS. The last service that we used is Route 53, and it's a DNS service, and it's a very simple service that we used for publishing web app EKS on webapp.smeapp.cloud. Monitoring an application on a distributed cloud environment is not a simple task, but thanks to Prometheus it becomes much more manageable. Prometheus is a monitoring application with a notification system that works by pulling various metrics from a series of endpoints in our cluster and in our application. For example, Payara web server by default has an endpoint /metrics where various information on the state of our application are shown. This information that Prometheus pulls from these endpoints on a frequency that we can specify are then stored in a time series database. The data that's stored in the Prometheus time series database does not mean much by itself, so we use the Grafana dashboard to visualize it better and make some sense of it. Grafana is an application that is often installed alongside Prometheus and it's used to visualize its data. In the picture that we're showing in this slide, we can see some of the statistics and the custom graphs that we created, such as the JVM uptime for our applications, and we can see all three components of web app, so web app, AS400 proxy, and H53, the number of live threads, the CPU usage of each component of our application, and many other informations. Not only that, but Grafana lets us create custom alerts that can work through email, Telegram, phone number, and many other notification systems. We created one for when our CPU usage reached over 90% of the capacity. And thanks to a Telegram bot, we received a message immediately when our cluster reached that specific threshold and when the load was below. So we could also know when the cluster went back to a more normal state. That was all we did for monitoring our application in a distributed environment. And let's now see the final structure of web app in a cloud deployment on Kubernetes. We can see that the users communicate through HTTPS with web app frontend. Web app frontend does the same with H253 service and AS400 proxy. All three components are located on EKS inside the AWS cloud. And finally, AS400 proxy communicates through TCP with our backend on IBMi, which is located inside the data center.
In the second part of this presentation, we will show how we change the architecture of this deployment, taking one of our microservices and installing it directly on the IBMi. To understand it better, let's take a closer look to this microservice, the AS400 proxy. It's the middleware of our distributed system, which manages the communication between the front end and the back end. The communication with the web app uses the HTTPS protocol, and the communication with the IBMi uses TCP. Now we see some technologies we used to develop the AS400 proxy. We implemented some REST APIs to interact with the services that this application exposes. Then we use the HTTPS protocol as we saw in the previous slide. We also implemented a Swagger interface in order to test the endpoints of this microservice. And we did this using the OpenAPI specification, which allows us to define our APIs through a standard syntax. In order to bring this microservice from the cloud to the IBMi, we used Quarkus, a Java framework developed by Red Hat. Quarkus applications don't require an application server such as Payara, and this allows us to have some optimizations. Indeed, we reduced the boot time of the application because we eliminated the startup time of the application server and the time the application needs to be deployed. Another advantage of using Quarkus is the memory usage. Indeed, Quarkus applications use 1/10 of the memory compared to traditional Java applications. In this slide, we see some differences between the two deployments of the AS400 proxy. In the cloud deployment, we communicate with the IBMi using TCP, while installing the microservice on the IBMi, we communicate directly on the data queues in localhost, and these improve the security. We have also less overhead because we eliminated the application server and the communication between extra machines. Then we take advantage of using the IBM toolbox for Java and the start current keyword. Using this keyword, when we specify the user for the connection to the IBMi, allows us to use a dedicated user for all the connection, and this improves the performance on heavy data transfers. So doing all these operations, we transform the AS400 proxy in an actual microservice. In this screenshot, we see that the user who started the application is the same system user for all the connections that use the AS400 proxy. And this happens because we specify start current in the configuration of our application. Now we will see a little demo where we will start the AS400 proxy from the Q shell, and then we will see the application running thanks to the Swagger interface. We prepared a bash script which sets some environment variables that are the configurations of our microservice, and then starts the application with the java jar command. Okay, we run this. And now we read the logs in order to check if the application is started. Here we see that the Quarkus application is started correctly and with our configuration. We have our credentials. Now we switch to the Swagger interface, where we can see the AS400 proxy is up and running, and we can also see the list of the endpoints that the microservice exposed. Finally, in this last slide, we summarize what we saw in this presentation with these two kind of deployments. The first one with 3 microservices deployed on the AWS cloud, while the second one with the AS400 proxy installed directly on the IBMi. And that's it. Thank you.